So as I mentioned before, the reason why this week's topic is a little bit different from what we have done so far is that the perspective that we are looking at is a little bit different. Okay, so usually what we're trying to do when we talk about the running time complexity is we look at how many times a statement is being executed. Okay, like the for loops, how many times the code inside that for loops is going to be executed. Okay, so that will tell you the running time complexity, and you will you can see what is the worst running time complexity and average as well as the best. So normally when we talk about the running time complexity, we always like try to find out what is the worst running time complexity for a an algorithm. Okay, so what we did this week is that instead of looking at the running time complexity of the algorithm, we are looking at how the input distribution is going to affect the cost of the running time complexity for the algorithm. Okay, so in a sense, usually what we want to look at is what is the worst case running time complexity, and when we use the probabilistic analysis, we can actually reason about what are the average case of that algorithm based on the input distribution the input distribution for that algorithm. Okay, and then we look at like doing the probabilistic analysis using the IRV, indicator random variable, whereby we can somehow say something about what is the expected cost, okay, for running that algorithm. All right. So before we start our tutorial, do you have any question in regards to our topic this week, class? So if we do not have, so as usual, let's go into our Google Drive and discuss over there. And please don't forget to sign your attendance. All right. So no questions so far. You just want to go. Let's just try and do the question tutorial and then see if we can do this. Okay. So there are two parts for this for this tutorial. What's a part two? So the part two. Okay. Oh yeah. Part one. Part one. There's two problems, and then we have part two. Okay. All right. So for part one, we are trying to apply the indicator random variable. Okay. So before we start, what is IRV in this case? What is it used for? Class? What is it used for? The IRV? Indicator random variable.
It's to represent what are the chances that you want to turn into like an expectation.
So what you're saying is like we're trying to find the chances. Do you mean the probability?
Yeah.
Yeah. Okay. So IRV is a method or an approach for you to somehow describe, like how you can convert probability of an event occurring into what are the expectation, is the expect value for that event to occur. Okay, and then basically that expectation we can somehow see how what are the costs, the probable costs that will incur based on the algorithm, as well as how the data is being fed into the algorithm. Okay. All right. Let's look at part one. So let's say we have this IRV A associated with some event A, and we can define IRV A as 1 if A occur, 0 if A does not occur. Okay. For each of the problem below, find what is the expected value associated with the problem, and then use the linearity of expectation, whereby if, like, let's say you have what is the expected value of event x plus y equals to expected value of x plus expected value of y. So this is what we mean by the linearity of expectation equation. Okay, provided that x and y are the IRV for an event A. Okay, so let's look at problem 1. Given a dice with 6 faces numbering from 1 to 6, find the probability of getting the number 5 when the dice is thrown. Okay, so in this case, we're trying to find what is the probability of a dice. When you throw a dice, we get number 5. Okay. All right, so 1, declare an indicator random variable for the event associated to throwing a dice to get number 5 for n number of throws. Okay, so someone have shared the answer here. Okay, so here let x be the random variable to get number 5 in n number of throws, and you define the IRV XA, whereby it is an IRV for getting number 5. So this one actually you can change it into IXA. Okay, is equals to 1 if number 5 is obtained, 0 if number 5 is not obtained. Okay. So this is how you write the indicator random variable for getting number 5 event. Okay, when throwing a dice. Anybody does not know how to get this? Are you okay with this one?
Yes.
Yeah. Okay. So for question 2, what is the probability of getting number 5 when dice is thrown? Probability of getting number 5 is 1/6. So again, do you know how do we get the 1/6? The 1/6, since there are 6 faces on the dice and 5 is one of the faces, and therefore the probability of getting 5 in this case is 1/6. Okay. And then what is the expectation of getting number 5 in one throw? Okay, so one throw from lecture slide 13. Okay, yeah. Therefore, we can say the expected value of A is the probability of A. And then the expected value of A is the expected value of getting number 5, which is the probability of getting number 5. Okay, so from the IRV that you have created here, so you can say that 1 times probability of getting number 5 plus 0 of probability of getting for not, this one is not getting. This one is not getting number 5. Okay, so therefore we can say that it is 1/6. Is the probability is 1/6 for not getting yeah, it's 5/6, right? Okay. All right. Okay. All right. So these are quite clear, right? It's pretty straightforward. So in a sense, in order for you to find out what is the expectation of getting 5 is 1 of getting that 5, and 0 times 5/6 of not getting the number 5. Okay. So this is from the slides. Yeah. Okay, so you get it from the slide. All right, so number 4, what is the expected value for getting number 5 in n number of throws? So if you remember, how do we use the IRV to find the expected value for several number of throws is that we try to sum up the expectation of all throws. Okay, what is the expectation for throw number 1? What is the expectation value? What the expected value for throw number 2? What is the expected value for throw number 3, and so on and so forth until throw n. All right. So the expected value would be the total sum of all the expected value of throws. Okay. So in this case, so therefore we know that the expected value of getting 5 is 1 over 6. So the total value of what is the expected value for n number of throws, okay, of you getting number 5 would be the sum of the expected value of the sum of 1 up until n of x a, whereby of you getting number 5 when you throw the dice. So, applying the linearity of expectation equation, so you can get this, right? So you can put it in, and therefore, we can find that, and we know that this is actually 1 over 6, right? And this will sum from 1 up until n. Therefore, we found that, so the final answer would be n over 6. Okay. Linearity of expectation. Yeah, that's right. Okay, so any question about this? Any question about this question? All right, so it's pretty clear, right? Because okay, so this is what I get because I think the previous group give me the probability of the dice whereby he or she add 1, 2, 3, 4, 5, 6 divided by divided by 6. Okay, so in a sense to get some average value. Uh, so please do not get confused what are the individual costs. What we're trying to look at is we're trying to look at the cost of the probability of getting the face, not the value itself. Okay, so if you're talking about the average, yes, you can actually do that. But in this case, when we do the probabilistic analysis, is we are trying to see what are the probability of that event occurring, not the value itself. Okay, so please take note of that. Okay, so let x1 be the number of trials until the first 5 is rolled, x2 x1 be the number of trials until the first 5 is rolled, x2 number of trials after first 5 that the second 5 is rolled. Okay, so basically here your friend did extend it a little bit. So what it mean by the expected time for the 5 throws is that it is equals to the expected time of the first row, expected time of expected cost for first row, expected cost for second row, and so on and so forth. Okay, so therefore, the expected cost for all 5 throws, let's say for example, the n is 5. Okay, 5 throws would be the sum of I equals to 1 up until n of expected of x of the event getting number 5, and therefore you get this one. Okay, so it's the same thing. All right, any question about this one? Anything you want to ask regarding the answer given by your friend here? Good. All right. Okay, so let's look at problem number 2. I think this one is from from the lecture notes. I think time I should like include one more example, because but never mind, let's do this one first. Okay, suppose that you need to hire a new assistant. Okay, so as you know, the hiring problem, whereby you need to you're a company that is using employment agency to find candidate for your company, and the strategy was you interview the person and then decide whether to hire the person or not. You need to hire employment agency, a fee to interview, as well as when you find out that you want to hire an applicant, you also need to pay more cost. Okay, and then you have to fire your current assistant, and yeah, as I mentioned, pay hiring fee to the employment agency. So you are committed at having at all time the best possible person for the job. Therefore, if you find that there's a better qualified candidates, you need to fire the current assistant and hire the new applicant. So you need to estimate the cost as the price for doing this. Okay. So the pseudocode for this, I think again you can find this in the slides. Okay, whereby you have the best, for like in the initial one. So we will set a dummy candidate which have rank 0. Okay, and then for 0 up until n, 0 up until n, not 1. So for I think this one is 1. Because we do not have 0 candidate, we definitely will how they call that, will interview someone, okay, for each of the for each day. All right, interview candidate I, and then candidate best higher, best is equals to 1, and then higher candidate I. Okay, so what is the running time complexity for this algorithm, class? It will be order of
O of n.
order of n, right? So what is the cost for this, depending on the strategy? The cost would be order of cost of interviewing candidates plus cost of hiring candidates, right? So do you see the difference? So basically, when you talk about the cost, you'll be looking at how is the input demand, the sequence of how your candidates is going to be interviewed during, let's say for example, during the 5 days, 5 candidates. So the cost will depend on the distribution of the candidates that you're going to interview. Okay, as opposed to the running time complexity for this particular algorithm, which is order of n. All right. Okay. So number 2, discuss the step by step approach on how we can estimate the cost. And then show you're working using the IRV and the expectation values. Can someone share? What is the answer for this one? Okay, so the IRV that we created is that we have the IRV X of candidate is hired. So therefore, we can specify the IRV of candidate hired is 1 if candidate is hired and 0 if candidate is not hired. Okay. So now since we have the IRV, what is the probability? So what is the expected cost for hiring candidate X? What is the expected value? Class? Nobody? Yeah. So it would be, so basically just like what we did for the, I think one of your friend sort of like do, whereby what we want to do is that, if let's say we have n number of candidates or I number of candidates, um, n number of candidates, okay. So whereby X is, so the expectation of hiring n number of candidates would be the sum of expectation value of hiring candidate 1, 2, and so on and so forth at the end. So the expected cost for hiring one candidate is 1 over I. Okay, so 1 over how many candidates do you have? All right, so therefore, the expected value of hiring n of if let's say we have n number of candidates would be uh think you frustrate me, give the answer, or you're trying to what? Okay, so basically this one, what you're gonna get is what is the one in between? The picture. I was trying to, like I know that iPad can actually annotate the screen, but I somehow cannot get um, my what to open on the web rather than open the Google document in my drive, Google Drive something. So inside the app, I cannot have that annotation. So it'd be much easier if I can actually annotate on the screen. But anyway, okay. So we have the sum. Okay, so we know that we need to find what is the sum of expectation of candidate one up until n. Uh, uh, of candidate I being hired. Okay. And then we know that the probability would be 1 over I. So I would be 1 over the total number of candidates that we have. And then the expected cost is, so actually this one, in before the linearity of expectation, the E is outside, but this one is after you apply the linearity of expectation. Therefore, the expected cost for this strategy would be the sum of expected cost for hiring each candidate. Okay, so therefore we get 1 over I. So the sum of 1 over I up until n. So this is a harmonic series. So from the harmonic series, you can get, it would be the cost would be ln n plus order of 1. Okay. All right. So up until now, because I think from our example, from the tutorial and the example that we have looked so far, it looks like the probability is either 1 or 0. Bear in mind, if you like try to look at other tutorial, talking about the probabilistic analysis of a probabilistic analysis, you probably may find that the probability value for that event occurring may not be just 1 or 0. Okay, so therefore, when you try to calculate, you have to take into consideration that probability value. So in this case, it's quite straightforward. It's quite trivial because it's either occurring or not occurring. Sometimes you may find that the you may find that there may be several events that you can describe. So if you look back at how the randomized algorithm randomized select algorithm being analyzed using the IRV, they try to specify all. If you look at the expansion of how they do the analysis, they did specify the condition on the size of how the possible size of uh, um, partition that a randomized select can have. Okay, so therefore, hence the reason why I don't really like go in depth into how the analysis is being done, but you can watch. I think there's one video by one MIT lecturer. Maybe I will share that one in case you want to follow through what happened when you use the IRV in analyzing the randomized select. Okay, but bear in mind there's a possibility of you not having just occurring or not occurring. Maybe there's a value for each of the event that may occur in your problems. Okay, all right. So up until now, I hope you understand. Okay, in terms of the difference about what does it mean the running time complexity of an algorithm, as well as the use of probabilistic analysis to look at the input distribution and you calculating what is the actual cost, not actual cost, but expected cost of that algorithm. Okay, according to, meaning we make an assumption of the distribution of the input. Okay, and normally when we make a randomized assumption, we assume that they are equally likely. So basically, the chances are all the chances are equal. All right. Okay. All right. So that is for part one. Any question about part one? Any question about part one? You good? Okay. Um. All right. Can you give me 1 minute? 1 second. 1 minute or 1 second. Yeah. Just for a while. I need to check on something. All right. So that is for probabilistic analysis. All right. So for part two is where we looked at randomized algorithm as well as order statistics. So we have looked into two algorithm for order statistic, which is randomized select and the select algorithm. Okay. So for question one, okay, so somebody already shared the answer for an iterative version of randomized select, okay, instead of using the question. And P left starting index of the array, R right starting, sorry, what is it? Okay, R is the right side index of the array. Q is the index of element that is being chosen as the pivot. K number or elements less than pivot? Not really. K is not the number of elements. Um, to some extent, it kinda like say the number of element, but normally K. But I would say K is actually the order statistic for what is the rank of that element inside the array. So if like let's say Q is 4, so we can say that the order of the order statistic for that value K, that value Q is actually 5. So it's the order statistic for that element. You get what I mean? Yes. So if like let's say the index that you found is let's say 4, okay, after you do the randomized partition. So K is the order statistic, the order for the element. So if like let's say the index return is 4, so we know that the index starts from 0, and you know the R is 0 up until some n. So uh, P is 0, R is some number. So Q minus P plus 1 should gives you 5. So therefore, if like let's say Q is 4, so the order statistic, the rank of Q is K, which is 5. Did you get it? Yeah. So the so K is the thing that we are going to compare with the rank that we are looking for. Okay, the order statistic that we are looking for. So if like let's say we want to find 7, let's say for example, out of that 10 element, and maybe since and then the K in this case is 5. So you know that the element that that you are looking for is not in the the lower subarray. So basically, it would be in the upper subarray. So the upper subarray, we are going to go. So if like let's say if I is equals to K, then it is, if like let's say you are looking for the fifth biggest element, then basically you have found it. All right. So if I is less than K, then you are going to then you're going to somehow either do the thing again, uh, uh, um, um, do the randomized partition again on either the upper subarray or the lower subarray. Okay, so this is the difference between randomized partition and in quick sort. Basically, you do the partition in on both subarray until it completes. All right. Okay. Any question for this one? Good. Yeah. All right. So for question number 2, suppose we use randomized select to select minimum element in the array A. You need to describe a sequence of partition that result in the worst case performance of randomized select. Okay. So in this case, we can say that what is the sequence of K that we're going to find. Okay. So the sequence would be um, uh, as we have discussed in when we look into quicksort, whereby the worst case may result if we somehow partition the array around either the smallest element, or as the smallest value, the smallest element in the array or the biggest element in the array. So basically, in this case, since we want to find what is the minimum element in the array, so we can say that the sequence of partition that will result in the worst case would be we partition around the maximum value or the maximum element in the array. Okay, so in that case, the sequence will be 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So it is just probably, since the array A looks like it is random, but somehow your random generator is very unlucky that it whenever that it randomly generate the pivot, it gives you the maximum. Okay. Yep. Yep. Okay. So that is when you will get the worst case performance of randomized select. It's similar with quicksort. Okay. you have to be so unlucky for your random generator to always generate the biggest element in the array. Alright. Or like somehow the way you, like, let's say for example, if you said like find get the middle element, like you never know how the distribution is going to be. Okay. Alright, so question number 3. How quicksort can be made to run in order of n log n time in worst case, assuming that all elements are distinct? Alright, so, okay. So n log n, quicksort is like we are trying to run quicksort like merge sort, right? In merge sort, the thing that cause it to run in n log n is because when it is dividing, it's dividing equally 2t over 2t n over 2. Okay, the division is like right smack in the middle, and we can get the n log n. And in fact, the quick sort, we can still get the n log n as long as we get some lucky partition. Remember when we discussed about lucky and unlucky, the lucky would be like, if like let's say you can get at least 10% on the subarray, you're probably still gonna get the n log n running time complexity. Okay, for the quick sort. But if like let's say we want to try to get it like right smack in the middle partition in the quick sort, we probably can do something. Okay, so here your friend have given the answer. Worst case, I believe that WCS is worst case. Depends on the selection of the pivot. Yep. If the pivot selection is one of the maximum element, the running time. Yep. Okay. So you are using medians of medians. Group of 5 having 5 elements. Find the median with the insertion sort, and then pick the median. Then recursively try to find the median of partition the array around this median. Yep. Yes. So basically what you do is that you find what is the median of the array and make them as the pivot, right? Is it right? So therefore, so basically it's like you are almost doing this like the merge sort. So since you get the median element for the array, you definitely gonna get like some kind of like a balance division between the subarray. So you can actually say that you are eliminating half of the array every time uh, 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 you do the partition. Okay. All right. Not eliminate half, but somehow the array will be divided into equal parts. Okay, rather than some may be shorter, some may be longer, and so on and so forth. Okay. All right. Okay. So that is fine. Okay, so for question number 4, so I had the feeling that we're gonna be quick for this tutorial, which is good. Okay, I think I need to somehow replay back on most of our lecture whereby we don't have any breaks. I'm so sorry. Okay, so question number 4, Professor Ole is consulting for an oil company, okay, whereby it is which is planning a large pipeline, try to run a pipeline from east to west through an oil field of N wells. Okay, so these are the wells. And then the company wants to connect a spur pipeline to the main pipeline along the shortest route, either north or south, as shown in figure 1. Okay. Given the x and y coordinates of the well, how should the professor pick the optimal location of the main pipeline? Okay, whereby it minimizes the total length of spur. So you need to show how to determine the optimal location in linear time. So answer? So what's the answer? I saw answer, so that's why I don't scroll down. So I thought somebody already gave the answer already. What is the answer? Any idea? How should we do this in linear time? Class? Hmm? Find the median of y coordinates. Find the median of y coordinates. Okay, so coordinates, y coordinates, how? Can you give me an example? Not example, but can you explain further? Find the median of y coordinates for all wells or for the furthest and the shortest. You get my question? You want to find the medians of y coordinates. So y coordinates of what? For the furthest y coordinate with the nearest y coordinates. Now the furthest and the nearest that y coordinates. Is that it, class? How do you think we're going to solve this? Any ideas? You have the right concept. So basically, since we are talking, no idea. Yeah, but you did say the median of y coordinates. But what are the y coordinates? Is it the y coordinates of the furthest well with the shorter the coordinates of furthest well, and then you have the shorter the nearest well, and then you find the median? Or is it that you find the median? Um, so each of the wells will have the y coordinate, and you find what is the median well based on the what is the how do you say that? What is the median well? What is the median y coordinates for one of the well? Can I say that? So there are different ways that you could be saying. Either you want to find the y coordinates between the nearest and the furthest, so you find the median, or you find the median of all the y coordinate between all the y coordinates for all the wells. So which one? Class? Or they are the same? Come, think. Nobody? No idea? Are you all thinking, or are you all waiting for answer? I hope you're all thinking. Okay. Okay, good. Would it be nice if, like we can, just like a PC where we know we are loading something or we are trying to process something, that's some kind of indication that we are thinking? Or maybe the screen would say that I like who is thinking. Features to have, like a camera that can actually detect whether you're thinking or not. It will be good feedback for whoever that is doing online teaching. I saw somebody write something, but I didn't get I was talking, so I didn't get to read what you were writing. Yeah, between those two, which one is it? Yeah.
Wait, doctor, you said between those two.
Yeah, because right now, yeah, when you talk about the median of y coordinate, it can be two. It's either you find the median of the distance between the nearest wells and the furthest well, or you find the median of y for based on each of the y coordinates of all the wells. Which one is it? I know you all have the answer. I want you to understand the answer.
Is it the second one, the latter, the oil, like each oil well, right?
Right? So basically, yeah. So to be honest with you, like I haven't tried like both ways, but since the questions say that we need to get it in linear time, so I believe we have to somehow apply the randomize something like select algorithm to find what is the median. So in this case, we need to have a value for this, and so therefore we can assume that not assume, but we can actually solve this problem by finding the median uh, uh, based on the y coordinates for all of the wells. Okay, so this is so that when the main line cut across through all the wells, it would be it should be dividing almost equally between the north and the south. Do you get what I mean, class?
Yes.
Yeah.
So is it like you want to minimize the total displacement?
Yeah,
Is it?
yeah. Because since we kind of like try to get it like somehow somewhere in the middle between all the wells, right? So basically we find what is the median of all the wells, and then we cut across the put the main pipe in along the median of all the wells. Do you think that would work? I think it will work.
I think so.
So
Because the oil
other
wells
than,
are from north and south.
yeah, it will be
The
from,
main pipeline is east and west.
yeah. So basically, what we are trying to do is that the main pipeline will go from east to west, and the spur would be from north to south. I'm very bad at direction, so please. So east to west, or is it east to west? East to west, north and south. Okay. So we know that our main pipeline has to cut across all the wells equally. Okay, so that's why one of the solution maybe is to find what is the median of y coordinate. So basically, if you find the median of y coordinate, you should be able to find one coordinate that will divide the well equally north and south. Does that make sense? Right? And then since it divide the wells equally, so you put the main pipe straight through, and then we assume that that would give the least total length of the spur. It might not give you the how do you call that? It might not give you the smallest, but at least it will reduce the length of spur, minimize the length of spur the total length of spurs that connects each of the well to the main pipeline. Is that all right? Yes. Is that all right?
Yes, that makes sense. Okay.
Yeah. So maybe somebody can write out the answer for your reference later. Okay. All right. Okay. Okay. So yeah. So we we only take 1 hour for our tutorial today. Before we end the class, do you have any question regarding your group project or anything regarding the topics before we end the class for today? Have you started doing the group project or looking to the group project?
Now
Sorry.
my group is meeting this weekend.
Okay.
I mean Friday, tomorrow.
All right. Okay.
For the group project, we have to do all problems, right?
If you want to get all the marks, you have to do all the problems.
Okay.
Because if you look at
Just
the, if
confirming.
you look at Yeah, because if you look at the rubrics, you will see that each of the problem will give you 5 marks. Um, 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 Additional would be the bonus one if you somehow able to use any algorithm that is better from the one that we have looked in class. Some marks you can actually get those bonus mark when you create your own conclusion. Okay, so the algorithm for coming up with the conclusion when you do the sentiment analysis as well as the, I think in the problem 3, so you can get bonus mark there as well because you somehow sort of like creates a new some kind of calculation there, some kind of process of reasoning about your conclusion. And the additional 5 marks is for problem number 4, where you have to look into a new algorithm called, I don't remember what is the algorithm. My brain always shut down after one. So for that, you can get marks as long as you are able to explain what is that algorithm is about. Okay, so if you can implement it completely, you will get the full 5 marks for that one. All right.
Okay.
Okay, so I have a question on chat. Sorry, I didn't see that one. The difference between these two methods, between which two methods? 249. So you mean like finding the median, is it? Law? Yes. No, there's um basically it's just how you try to determine how which method would give you the most minimized total length of spur. I haven't tried like having like an example of like if like let's say I'll take the furthest one and the nearest one and try to find the median of that distance. But I would say that there's a possibility that the median will not cut across the same number of wells from the south and from the number of wells north and south. So if like let's say for example you have one well that is much further from the rest, so the median may be will cut more on will get you more wells on the south, let's say for example. I haven't tried if it is actually going to make any difference. All right, but one of the solution is that I mean logically, if we can actually uh, divide the wells from north to south, we assume that we can minimize the length of the spur for all the wells. Is that okay? Is that clear? No? Yeah. Okay. So if there's no more questions, so I guess I'll see you in the lecture next week. So I don't remember what is the topic for next week. I think the topic next week is hash table. So since I think most of you have looked into using hash when you do the Rabin Cup, when you do the lab. So most of the concept, like let's say for example, the reason why you need to choose the prime for the hash, like that how do you call that, the how do you choose the prime number for the hash function that you use. So all of this concept will be explained, hopefully, or discovered when you go through the hash lecture next week. I think it's going to be hash next week. Okay. All right. So
Okay.
in that case, let's end the tutorial for today, right?
Yeah.
Yes, 1 hour only. Yeah,
Thanks,
finally
Doctor.
we can we can cut short our class. I remember we always like use the full hour of
Yeah.
our class. Okay, so let me start recording first. And okay, so I'll see you next week. Bye.
Right.
Assalamualaikum.
Bye, Doctor.
Bye. Bye.